when he was doing fieldwork in Orissa. I was doing fieldwork for geology. He was doing fieldwork for agriculture. He and Paria in the state circuit house we met. So, I mean, the story goes like this. See, what happened is, so sometime around 2000, early 2000, we came out of Pathro scheme and we started ordering data in square kilometers, which became much cheaper. Then slowly, after 30 years of this game, the whole analysis changed because the NRSA had one Bendix system. But our NRSA guy used to go to IBM 370 machine in IIT Chennai to take printout, spread the whole map, print black and white printout characters, and identify which scan line, which this thing, training sites, So we used to always say, they will say, today Thiruvenkatacharya has booked the system. You can't come this side for 3 days. He was doing NDVI, using Nova data. And that is where the RRSS came into picture. ISRO realized we should have regional centers. I mean, under the aegis of NNRMS, they were all there, the apex guiding. So the SEP systems came with the idea of providing digital facility to the users in that region. So, of course, RRSS did many more jobs. So I am proud that I saw the entire growth because I joined in 1975, used, the volcano scanner, analog thermal scanner data over Western Ghats. Then InterASAR and SAR-C data. InterASAR, we paid money and got certain areas surveyed. Shuttle imaging radar C data we procured. Then the Kate 6 and MKF6 and Kate 140, Rakesh Sharma's photos. Then our own aerial photos, then satellite. So I have gone through the full transition myself in my own hands. But like PPN Dr. Nageshwara used to say, still we were as pencil scientists. Now this pencil paradigm has now completely got shifted into pixels. But now, in the next 20 years, that is 2000 to 2026, too many things have happened across the world. The Earth observation satellites are no more the property of the government. The constellations have come, the total scenario is changed. The International Charter on Space and Major Disasters is no more valid because anytime, any place on the Earth, you get data. Satellites have become smaller. Launches have become much cheaper. And everywhere, if space policy or remote sensing data policy has been liberalized. So today, the user doesn't want data. When you go to a user, don't say, this is the data cost, analysis cost, this cost, that cost, interpretation cost. No. Users today want solution. Okay. Intelligence as a service or information as a service, IaaS, that is what you want. Even satellite as a service, that is slowly going to disappear. A user, you say, I'm a farmer, I grow crops. In this season, from my day of farming or sowing till harvest, the insurance company says how many times he would like to have monitoring information. You give me data, how well is my crop doing, whether there is any failure of monsoon, whether there is any drought situation. So, of course, a lot of ground data is getting integrated. Now, that is also not the end of the game. See, everybody wants today analyzed solution better if they are not made to hear about data. I have to buy Sentinel data, that data, there is a catch. No. Give me analyzed information, whatever, whether it is urban infrastructure, whatever. So today it is geospatial intelligence and geospatial economy, where you take care of integrating the remote sensing data with geospatial tools, AI, VR, whatever. Now people have gone a step forward. They are adopting edge computing, even in small, 6U, 12U kind of satellites. You see, if you want to know real-time information on forest fire, you don't have to get the entire information. The forest department wants to know which exact compartment there is fire. So the edge computing chip, which they would have put in that satellite, will take care of the forest, and there will be automatic alerts. So basically, I must say that having got into a field by accident or by choice, otherwise, I wanted to become a mining geologist, having studied geology. I worked at 7,600 feet underground also in Kolar. But 1 month I thought it is enough. Came to Karnataka government, worked for just 14 days on the ground by the time I got into NRS and walked through the whole ladder of remote sensing, the way it, it grew, it began and it grew in ISRO. And of course, these days it is beyond me because the computer people, the AI people, they have taken up. But the concept wise, we are pretty clear. Like, Dr. Navalgund always talks. Be clear about the concept, what exactly you are doing, what is that you want to. So that is the whole thing. And our signature appearance of those days, if you are going to Delhi, we should carry one roll, bamboo of satellite image, and whether it's the minister, whether it's secretary, government of India, you should open the roll and spread. Even in Indian Airlines, the air hostesses used to recognize the ISRO, you get it, because that bamboo is there, That was our signature. Now today it is laptop, MacBook Air, MacBook N2, N3. So that is the transition in our own lives, and that is the transition in remote sensing. So I don't want to tell more. Where it is heading further, we all know, and we are eager to hear Rashmi ji, because I know her from her very young age, pretty dynamic, pretty focused. So we are looking forward to, and hearing on NISAR is something, the most expensive satellite ever built in this world. And lots were talked about, its capacity for monitoring the mobile phones, the earthquake, things like that. So hope you will be touching upon them. And thank you once again for having me with you this afternoon. It's a great privilege. Thanks a lot.
Thank you, sir, for bringing us to a new vantage point of pencil to pixel. It is an honor for me to introduce our chief guest, Dr. R. Navalgund, a true stalwart of India's Earth observation program, whose vision and leadership have shaped the course of remote sensing in this country for over 4 decades. He served as director of National Remote Sensing Agency and thereafter as director of Space Application Center, overseeing the development of sensors and payloads flown aboard India's Earth observation and planetary missions. He has represented ISRO and India at the UN Committee on Peaceful Use of Outer Space, the Group on Earth Observations, and the Committee on Earth Observation Satellites. A man whose name is synonymous to ISRO's Earth Observation Program. Ladies and gentlemen, please join me in welcoming Dr. R. R. Navalgund, our chief guest, to address the gathering.
Good afternoon to everybody who has assembled here. First of all, I would like to compliment Dr. Thomas for taking this initiative and organizing this talk. I think that's very important that people from different institutions engaged in the use of remotely sensed data for various applications and science can come together and interact. I would like to also compliment Dr. Girish Pujar uh, for taking the initiative and accepting to host this particular event at this place. I think that's very important. Institutional support has always been important for the society, for the professional society to organize this. I'm very happy that a large number of people who have been engaged in different aspects of particularly the synthetic aperture radar, NISAR, are here. I'm very happy to see Chaitra, the project director of NISAR. I'm also very happy to see our other colleagues, Dr. P.P. Nageshwar Rao, Ganesh Raj, Arunachalam, and there are many. Kulkarni, Dr. Who is synonymous with cryosphere, not only in this country but also in many he has made a name for in what is that? Pontification Academy of Sciences, Vatican. And I'm very happy that my colleague and friend from Space Application Center, Rashmi, is here to talk to us about NISAR, particularly its science, which is very important because now I don't think in ISRO should be talking about application because that is anyway taken over by many in the country. There are many organizations which do, and in fact, many of the stakeholders themselves do applications. Our job is to get into the science of any of the instruments or measurements that we make in ISRO or elsewhere. So I'm very happy to be here to listen to Rashmi Sharma on this particular topic. And I hope the RRSSE, the first since there have been many people, Uday Raj, P.P. Nageshwar Rao, Hebbar is not here, I'm not seeing him, but Ganesh Raj is here. So many, Divakar, so many of them have contributed to the development of regional remote sensing, which was earlier service center and now it is only center, no service, right? So that means they are going to do only developmental research, science related work. So with these few words, I look forward to the talk by Rashmi Sharma.
Thank you so much, sir. Before we begin, I'd like to take a moment to introduce Dr. Sharma to you all. Dr. Rashmi Sharma is Deputy Director of Earth and Planetary Science and Application Area and an outstanding scientist at the Space Application Center, ISRO, Ahmedabad. He has played a key role in missions including OceanSat-2, SCATSat-1, Saral Altica, and today leads OceanSat-3 3A as Project Director, Utilization Program, and serves as Science Lead for NASA ISRO NISAR mission. She is the recipient of P.R. Pesharoti Memorial Award and Satish Dhawan Award of the Indian Society of Remote Sensing, with close to 110 publications in peer-reviewed journals. Dr. Sharma will speak to us today on NISAR mapping Earth in motion. Ladies and gentlemen, please join me in inviting Dr. Sharma for her keynote address. Ma'am.
Thank you, Abhinav. And first of all, very warm greetings to all of you on this very beautiful day, which happens to be the birth date of our founding father, Dr. Vikram Sarabhai, and which we celebrate very fondly as the National Remote Sensing Day. So, warm greetings once again to all of you. Uh, Actually, words are falling short today for me because I'm sitting next to my mentor, Navalgun sir, and I can't express how happy I am actually, sharing the display with sir and sitting here talking about NISAR. He has been my mentor. I have seen him, looked at him, and I have grown in my career. Thank you, sir, for everything. And equally very happy to be with Hegde sir and Dr. Pujaji and with all of you. And once again, very warm greetings. And I'm especially happy to see so many young students, colleagues here. So I hope something which I'm going to convey to you will make sense out of my presentation. Uh, well, I'm going to talk about NISAR, which is, of course, well known as NASA ISRO Synthetic Aperture Radar. And this topic was suggested to me by Dr. Thomas D. and Sir that I should talk about mapping Earth in motion. So when I just thought about it, that how to start this actually, because we all know Earth is in motion actually. There's nothing new in that. But then I thought, no, let me give it a context in some different perspective, in the perspective of NISAR mission. So you are sitting here, I'm sitting here, but we don't realize, that the Earth beneath our feet is actually very restless. It's shaking. Glaciers are moving, flowing. tectonic plates are shifting, cities are sinking, and all these are happening without our realization, right? You can't see, I can't see. Even the best of the optical cameras in the orbit can't see them. Okay. So, well, then what is the answer for it? So the answer here is NISAR. Okay. So this is the mission which is orbiting this planet, and it is going and it is measuring actually the deformities and the heartbeat of the frozen yet solid uh, planet in which we are staying, Earth. Okay. So, and it is doing it at such a high precision that it was totally unprecedented, actually. Okay. So that is the beauty of this mission. And just to give you some more context in this, for this mission, you know why this mission is very, very important? Just 2 days back, there was a earthquake which happened in Colombia, right? And it was so devastating. So many people lost their lives, and so much of damage happened. And these events are becoming more and more frequent now. Be it, the solid state disasters, solid earth disasters, or even the extreme weather related events which are happening, maybe flooding, sea level rise, and many things. And this is the mission which is going to help us understand all the physical processes, so many new learnings and many new unlearnings also, because it is going to help us prove some theories and disprove some theories. So we are all looking forward to for this data to come in a as a long time series. Already the data has started flowing. Okay, can you go to the next slide? Yeah. Well, I think I have already talked to it. So what I'm going to present in my talk today is that NISAR is actually it's going to be a paradigm shift in the Earth system studies. Okay, maybe from the technology. I mean, you talk from the technology side, the kind of instrument advancements that has happened. You talk about science, the kind of shifts that you are going to track from this mission, the safety that you are going to address. It will help you predict many of the hazards, actually. So early warning, forewarning aspects are going to be understood by this mission, the data which is going to come from this. And one of the key aspects of this mission has been the collaboration. Okay, the shared collaboration, the mutual learning collaboration. And this mission has proved the key for the collaboration, actually. And the international collaboration, we are going to also now take it to the national collaboration. We are having many projects in offing to address many of the outstanding signs. Can you go to the next one? This is a slide which actually I thought I'll put it for the perspective. You know, this mission was destined to happen. Why I say destined is because that destiny was the starting point for this mission, and this destiny mission was actually planned by NASA in the year 2007, because NASA works on any instrument based on the decadal survey that they conduct. So the decadal survey that came out in 2007, the scientists felt that no, there is a need to come up with a mission which can help us understand many of the disasters related to the ecosystem, or related to solid earth, cryosphere, and also many of the climate change impacts. So they had already made up their mind that no, L-band synthetic aperture radar with many new features. Not that L-band was new to Destiny. Before Destiny also there were many L-band missions were there. But there were many new features which I'll just talk in my subsequent slide. And they had already planned this, that they are going to come up with the L-band synthetic aperture radar mission. Now what happened after that? Thousands of miles away from that continent, okay, ISRO was also silently working on developing the C-band radar technology. And this is one of the very, useful example, very meaningful example which I give, is that, they came to us because we were already developing the technology, the SAR technology. And then there was a discussions, and formal international agreement was signed in the year 2014. And with the understanding that they will be having this L-band SAR, ISRO will be coming up with S-band SAR, and spacecraft and launch will be all ours. And rest is all history. July 30, 2025, that is the last year, it was a historic day when this mission went in orbit. And subsequent to that, it's been 1 year, but 1 year we were not sitting quiet actually. You will be wondering that, you are not yet able to see the data and all. No. After the initial, the orbit stabilization and many testing and everything, there was a commissioning phase. So during the commissioning phase, we tested all our algorithms. We did a lot of calibration activities, and we saw that yes, the data sets are all perfect, and we are now ready to come up with the science products which we can release it later. So very recently, this month itself, there was a 1 year event which was celebrated jointly with NASA JPL team and with ISRO team, and data became operational. 30 TB of data product is what every day it is being generated at our NRSC Bhunidi site. So you can imagine the kind of and the volume of the data that this mission, and this is alone only from S band. I'm not talking about L band because that's much more huge data sets. Okay. So, well, and can you go to the next one? Okay, so I thought that, many of you would be wondering that what is so special about, this NISAR when there are so many other synthetic aperture radar missions already in the orbit, and SAR is not new to the global community actually. It came as a pleasant surprise to me that this L band, which we talk very fondly that L band SAR, no, L band, the first SAR mission was L band actually, CSAT in the year 1978, which NASA flew. And why this CSAT is very close to me is, I had joined ISRO in 1991. And at that time, my guide, he told me that, why don't you look at the altimeter data? And altimeter data was coming from CSAT and GeoSat. So those two were the missions. So I looked at the data from the CSAT and also from, the GeoSat. And that is how I came to know that CSAT was the first SAR mission having the L-band capability. Of course, with the limited capability that the SWAT was only 100 kilometers and 25 kilometers was the resolution. Unfortunately, it worked only for 100 days, but it paved the way for the synthetic aperture radar mission. And after that, there are, I may not talk about all this. All of you know that most of the space agencies have launched radar missions in one way or the other way. And at ISRO, we are not lagging behind. In fact, we have an extremely good contribution in the global constellation as far as the SAR mission is concerned. RISAT is one such example. And we have now many frequencies. The SARs are working in X band, C band, LNP band. There are many actually. So all the suite of frequencies are available, the data sets. Next one. Well, this is a slide which again is very close to me. When I was working on these slides, I thought that no, this I will tell to at least for the younger people, the students who are here, that this will tell you that SAR technology has never been new to ISRO, and we have been working on this technology for many years actually, and in a very systematic way. Sir knows everything. Sir has been the pioneering in many of these missions, which I'm listed here. First proof of the concept mission, as far as the ISRO demonstrated, was the C-band airborne SAR. Okay, and then some of the critical technologies were actually demonstrated through the DMSAR, which was the disaster management SAR, which was again flown for many of the disaster mapping, especially the flood mappings. And it proved to be a workhorse actually, because many of the floods were mapped using the airborne campaign. These two missions paved the way for the first spaceborne mission, RISAT-1, C-band, in the year 2012. And it worked for 5 to 6 years. And meanwhile, we were working for LNS band dual frequency SAR, which was launched for the planetary missions. And here again, it gives me very, feels me proud to say that this is the first planetary mission, okay, by any global agency to have launched, this dual frequency and with such a high quality data set, okay. And parallelly, we were the technology side engineers were miniaturizing the system, and then many things were happening. And we have now operational RISAT-1A, and then parallelly we flew this LNS technology. Also, we developed. We flew on airborne, and then NISAR came. while our teams were working on the developing this technology, the other team was not sitting quiet. Actually, they were there, or they were already developing P-band airborne SAR, and many of the campaigns have already happened actually. So maybe in future you will see a P-band SAR from the ISRO side as well. Next one. Okay, so now I'll come to the science part of it, and this is the India map. Okay, the reason why I'm showing you this is that the NISAR matters in the Indian perspective a lot. While we are very proud that we have a lot of resources, we have very good biodiversity, we have so many glaciers, many things. We are blessed with seasonal rainfall, monsoon rainfall, but we also suffer from many disasters and we are facing many challenges. And all those I'm not going to read out. Some of them just I'll read out, like flood, landslide, earthquake, glaciers, declining. All these things can be monitored and are being monitored using the NISR data set. Okay, next one. So this I will not talk in detail. There are many new technologies which were developed for in the context of the NISAR. The earlier days, the problem with the SAR mission was very narrow swath we used to get because we wanted a very high resolution. So there always used to be compromise on the swath and the resolution, spatial resolution. That's a pixel size. Okay, which Hegde sir mentioned. So that is the pixel size, which here also it matters. So there always used to be a compromise. So strip map gave very good resolution but limited swath. Then came the ScanSAR technology, which gave us good swath but compromised on the spatial resolution. So to make to combine this strip map and ScanSAR came the newer technology SweepSAR, and it's a very advanced technology, very innovative technology. I'm not going to go in detail. But in this one, you can see a bigger region. At the same time, you can get a very high resolution pixel. And the third element is you can get a very good signal to noise ratio. That means the signal strength is also very good. So all three things you are going to maintain from this SweepSAR technology. And this NASA developed it. And this is what has been put to use in the NISAR mission. Next one. So from the technological advancement point of view, this is SweepSAR. Okay, I would have loved to talk about that, but for the want of time, I'm not. If any of you are interested, you can talk to me later. I will explain you a bit on this, how this works. And it has dual frequency, L-band by NASA. S-band system was developed by our colleagues here at ISRO. And there was a digital beam forming because so many of returns are coming. So on board digitally, the beams were formed to get a very high resolution. And this is another fourth bullet is another very important point actually. So far, most of the missions, most of the SAR missions, they were not giving us the systematic coverage. But this is the first mission which every 12 days systematic coverage is you can get. At many places, if you combine the ascending and descending passes, you can get even 6 days of repeat cycle. Okay. And then there are another technological things, technological advancements like pulse repetition, dithering to avoid any gaps in the measurements, full polarimetry, quad pole, and everything you can get from this mission, which you can think of in terms of measurements and interferometric capability. And there is another beauty of this mission is the 12-meter unfurlable mesh antenna, which is one of the largest antennas which has been ever flown. So these are some of the newer technologies that has been, and the right side, what you see is, the payload, which was in the lab, and you can see the kind of complexities and kind of electronics that are being displayed here. Next one. Okay, so this I have already talked about. So L-band, the beauty is it has a wavelength of 24 centimeters, so it has a greater penetration. So beneath the tall trees also you can see the surface. So that is the advantage. S-band has another set of advantages, which you will see later. And with the 9 centimeter wavelength, you can still see the vegetation. I mean, beneath the vegetation, the ground, but with the lighter vegetation and the shorter crops. So another thing is 240 kilometers swath, which is again unprecedented one. And orbit accuracy is fantastic because in order to measure the Earth's movement, which are very subtle, very few millimeter, centimeter level of kind of movement you are watching, I mean, you are trying to map. So obviously you have to have the orbit accuracies are very precise. And This is another beauty of this mission. And just to tell you that, after the commissioning phase over, and then we did a lot of calibration exercises. We tested the data. We have a very good pan-India calibration sites distributed, and more than 25 cycles of the operations has already happened. 20 TB of data every day is being generated at our NRSC Bhunidhi site. And on the right, what you see, the table, there are 9 types of data products which are being generated every day, okay, right from level 0 to level 2. And there are different sets of data sets. I will not go into the detail because, the covariance data set, unwrapped data sets, there are many different types of data sets which are available. Next. So talking about the science, this is the major drivers of this mission was cryosphere from the NASA side. Okay, from the US side, the drivers were, why I'm telling US side is there is a reason for that. I'll just tell you. See, cryosphere, solid earth, ecosystem, and water. Okay, water means your hydrology and soil moisture. So these were the 4 driving signs or the forces for this mission. But what we told them that no, we want to get the observations even over the oceans also, because India is surrounded by Arabian Sea and Bay of Bengal, and this is a mission. We should also get good amount of data sets we should acquire over the Arabian Sea and the Bay of Bengal side. And I'm happy to tell you that though, the systematic data coverage is there now in both the sites, towards both the sites, and also at some of the sites near to the US coastal sites also. They were not initially ready to get to acquire the data near to the US coastal regions. But we told them, no, it is needed to test many of the algorithms, and many of such sites are now identified and the data are being acquired. So these are the science objectives. Of course, one is when you talk about the ecosystem, then forest and wetland ecosystem, how much carbon is stored in that? That is very, very important, okay, to understand because, these forests and wetland ecosystems are the major source of carbon sequestration, actually. Whatever the carbon you are dumping in the atmosphere, they are being absorbed by these systems. So they are protecting us. So it's important to understand that. How the mangroves or alpine ecosystems are changing due to the climate change, that is another science driver. Okay, whether there are any changes in the cropping patterns. So this mission is going to help you understand that as well. How much land is inundated? What is the soil moisture? Because soil moisture is another very important parameter for the you talk about the agrometeorology or for the drought monitoring or for any such thing, flooding. So all those parameters you can get from this. Snow water hydrology is another aspect which this mission is going to help us. Ice sheets and glaciers. Glaciers are melting and because of the stress due to the climate change. So how much it is melting and like how much it is getting, converted, how the hydrological balance is getting affected. So all those things. And yeah. Yeah. It's there, sir. Just after this. Just after this. Yeah. I'll show you some here. But just after this, you'll see many such, I'll take you to the tour of those slides. Okay, yeah. And one of, no, sir, perfectly fine. And one of the major drivers of this mission is earthquake, landslide, and land subsidence. So this is what it is. Of course, you would be wondering that, many a times we have been told that, can you predict earthquake? Okay. As of now, I would very firmly say that no, you cannot predict the earthquake, but you can definitely understand the processes behind those earthquakes, which will help you in setting up an early warning or forewarning system. So that is also very important. Or the risk assessment you can do, vulnerability assessment you can do. Okay. And then the last science objective which I have written is, of course, close to me as well, because I happen to be coming from the ocean side. So I'm very happy to tell you that we have seen many, many beautiful internal waves in this, in this data sets. I'll show you that. In order to achieve these science objectives or to, address these science objectives, we have planned 11 science products. And again, very happy to share with you that most of these 11 science products are now being generated at the Bhunidhi site for any users to download and to have a look at them. So forest develop, ground biomass, mangrove cover, active crop area, land inundation extent, how much is this land is inundated due to the flooding, surface soil moisture, all these products now you can just browse through the Bhuniri site and you can get a feel of that. Yeah. Next one. Okay, so collaboration is the key. Collaboration has always been the at the heart of this mission, and we are now extending this collaboration to our national institutions, and we are engaging with many of the academia research institutions. We have in-house NISA utilization program, and through this program we are engaging with many of the institutions. And of course, in the given space reform that happened, we are engaging also with the non-governmental entities, private sector. We had a very good meeting last year at Space Application Center, and a lot of seed money has been given to many of those startups as well. And we are planning to conduct many of the capacity building, next one. So this is where we stand as far as our readiness is concerned. So we have now 53 proposals from 41 institutions. They are all funded, and 45 proposals are in-house. But 53 are under the announcement of opportunity and also in the collaboration as a collaboration need. We have many MOUs we have done to make use of Survey of India course data sets for Survey of India and many other things are there. I mean, these corner reflectors for the calibration that you see all across India, they were actually designed and designed by us. So these are all the important milestones which led to this mission, and now we are ready with these data sets to make use of those data sets for addressing those signs. Yes. Now the data has arrived. Next one. Yes. So now I'll show you some of the results quickly, very quickly. Next one. Yeah, and this is a Bhunidhi site from where you can download the data. Yes. So this is the beauty. I mean, it's very surprising to see these colors, because usually the colors are seen in the optical images. But so many polarimetric measurements are available, different types. You can make such color composites and beautiful colors from the SAR data set also. So these are the nicer polarimetric decomposed data sets. And you can see the left hand side, there's the null, you can see the Null Sarovar, which is a Ramsar wetland site actually. Then Antarctic glaciers, you can see beautiful glaciers, and then how those crevasses are seen, and those icebergs, small icebergs are also in the ocean, you can see. Then Hoshangabad region, what you can see is, there are many such features. Of course, the rivers meandering and the water bodies are very distinct. But apart from that, you can characterize the surface in terms of tall crops as a even bounds, volumetric scattered regions, buildings, many more things actually. So yeah. So this is one such colorful image which I thought I'll show you for distinguishing many surface features in this one. Next one. Yes, this is a very important product which our colleagues have generated. This is 100-meter soil moisture product. It was actually unprecedented. No other instrument can give you in one cycle pan-India soil moisture at 100 meters. With RISAT, we used to derive this soil moisture product, but that was at a 500-meter resolution. This is at 100-meter, and you can see this is one cycle composite for the entire country. And of course, we have checked it accuracy also. It is meeting the targeted accuracy. So with the 94% accuracy, we are able to derive this product from S-band. And whatever results, by the way, I'm showing you, it's all from S-band actually, from our own sensor. And those are the 4 regions where you can, those are the blown up regions, and you can see much more finer details of the soil moisture variability. Next one. Well, this is just showing you the time series, how for the 8 cycles, how the soil moisture is changing. And on the right side, what you see is the reg plot. Basically, it tells you that, how in time the soil moisture peaks are shifting and changing. And that. This is the Ahmedabad region, actually. Next one. Yes. Now, this is another product, same product, but this is at a 10-meter resolution. Actually, in one of our discussions that was happening, one of our seniors says that your satellite is, your sensor is giving you 10-meter resolution. Why are you deriving the product at 100-meter resolution? We said, no, there are some limitations. We cannot go to that kind of a. He said, no, you try. So we tried, and thankfully we could get extremely good field level soil moisture product from this. I mean, you can see the kind of variabilities in the soil moisture that you see in these images at 10-meter resolution. And all these algorithms are all developed in-house actually from the physics point of view. From the first law of physics, we have developed this actually. Next one. Next one. Just go back. Yeah. So, and this is just one site over the California region where we thought that let us check how our S band compares with the L band. So you can see the bottom two images, our S band soil moisture at 100-meter and L band soil moisture, which they are deriving, they are matching pretty well. And the detailed analysis we are still, performing. We just want to see that whether by combining L band and S band, are we able to get some, the better accuracies also. So that is also undergoing. So that activity we are doing it to combine those. Maybe we are thinking that those regions where the crops are, shorter heights, maybe S band will perform better. But we need to check that actually. We need to work on that. Next one. This is annual forest above ground biomass. So this is another very, very important parameter in terms of carbon sequestration. How much carbon is stored in these dry mass actually? That is what it indicates. And happy to show you that this product is also now operationally available from the Bunidi site. Next one. Yeah, this is a active crop map, and basically it tells you that how much area of our country is right now under the cropping area. So this and a long time series, if you check this, it will also tell you some indication. It will give you about how the cropping patterns are changing actually. So this is active crop map, and those are the sites which are the blown up sites from the bigger picture. Next. This is forest disturbance, although forest disturbance was supposed to be mapped after the year, but I told my colleagues that, okay, it doesn't matter. Just with 3-4 months of data set, let us take one region and see that whether there are any disturbed areas. And we could see, in this Haldwani, that Uttarakhand region, those hotspot regions that you are seeing are the forest disturbed areas actually. And on the right side, the mangroves cover also we have mapped. And most of these products are matching what the accuracies which we had targeted. For some of them, yes, we need to work more. Like this one, mangrove cover, we need to work more to match better accuracy. Next one. Yeah, this is the recent Brahmaputra flooding, and you can see all those red patches that you are seeing are all the flooded regions. And this is how it helps you actually every 12 days, systematic data. So it will tell you, give you the flood inundated areas, and which will help you in modeling the flood model and even in forecasting also actually. Next one. Now coming to the cryospheric science. So these are some of the glaciers faces which we have mapped using S-band. And once again, happy to tell you that whatever the classes which we wanted to classify, we are able to see them in these images, and we are able to classify them as wet snow, bare ice, percolation zone. So all those classifications, we are able to do that. With, of course, with 70 to 90% accuracy. We need to bring that 70% to 90%. So we are working on that. We are waiting for the reference period, to get more data sets. Next. These are glacial ice velocity. You can see very nicely over the Gangotri glaciers, and even in the East Antarctica region, you can see how the ice velocities are changing. And very nicely, again, it is bringing out these glaciers when it is hitting the sea, what is the velocity, and in the grounding zone, how the velocities are again picking up. So all those things we are able to see in these map in these images. Next one. This is again polar sea ice drift. This is one of the very important parameter which we give to NCPOR, which is the Ministry of Earth Sciences Center. During their Antarctic expedition time, they are very much interested in knowing that how much this sea ice are drifting or breaking, or because it helps them in routing their ship navigation. Next one. These are again ice sheets. I will just quickly go through. You can see beautiful, even the volcanoes are seen in the ice sheet regions. Of course, these are dead volcanoes, but you can very well capture them in S bands are. Next one. Yeah, so this is what we have been waiting for all along, that whether it is able to, see the deformation, the kind of deformation we wanted to see, NISR to see, whether it is able to bring out. And again, you can see that very nicely. I mean, the L band and the S band both. This is for the Balochistan earthquake, which happened on 13th February. And you can see that from the fringes, the upper figures are showing on the right, are showing you the interferogram, which gives you the fringes. And from those fringes, we derive the line of sight deformation. And the positive values in the line of sight tells you that, the surface is going up, shifting up, and the negative side tells you that it is going down. So nicely, all the deformations are brought out, and both are matching pretty well, actually, the L band and the S band. Next one. This is another example of the, of the volcano, which happened in Indonesia, is known for many active volcano regions. So one such example, you can see it here. Next one. And this is a landslide, actually. Two landslides, one in US and another in India. We have seen both the, these landslides. We have mapped it. I mean, very nicely, the S band, L band, all are bringing out those kind of, those movements, actually. Next one. This is now coming to the ocean side, and actually, there's I would say there's nothing much new. Many of the SAR missions can give you, these oil spills and internal waves, everything. But the beauty of this mission is on the left side of the image. This actually I could see only just 2 days back. This is one image where if the winds, these are winds actually, which have been derived from the S band. So if the winds are, encountering any small islands, so what happens is because of those, obstruction, there is an effect called funneling effect actually. So the winds get trapped in a smaller region and their velocity suddenly increases. So all those patches, the green, dark green patches that you are seeing is because of that funneling effect. And this is very, very important for, it generates the turbulence in the air. So many a times the airline, for the aviation sector also, this is a very, very important input. And and so beautifully it has brought out to those, the winds are going from 10 meter, 11 meter to 16 meter per second. All those small, narrow bands which you can see. Even the left hand side, two small islands below, they are also creating the funneling effect actually. Okay, so this is, and all these products you can see. And by the way, this winds are also now, dockered into the Puniti site, and now we are going to generate the winds as well. Next. This looks like my last slide, where we have shown that how L and S band in a joint processing mode, what it can bring out. And you can see, I mean, as expected, wherever you have the shorter crop regions and agricultural field, the S band becomes, I mean, it shows more sensitivity. And those regions where there are tall crops, actually, so there the L band is more sensitive. It was expected, but it is very nicely brought out in this composite image as well. Next one. Next. So now we have all suites of frequencies in the orbit, actually. We have mission with X band, we have mission with C band, we have S band, L band, P band, biomass is also there. And this is the best time for the SAR community to use the SAR data, because I don't think, I mean, such a suite of data set was available in earlier days. So by combining this, many new science and, many new products can come up. So soil moisture is one such example. With P band, you can see the root zone soil moisture. With XC, S band, very surface. L band still has a good penetration. So our scientists are actually trying to combine these all frequencies and to see the science that they want to bring it out in terms of the sensitivity and in terms of the penetration depth. So combining that. And my last slide is next one. Yes. And NISR is not the only great technology in the orbit. There are other missions also. So, and the beauty is in making synergistic use of these technologies. Three such technologies which I'm actually personally very fond of. One is the SWOT mission, surface water ocean topography, interferometric altimetry. Another is the NISR mission, SAR, very advanced SAR. And the third one is the PACE mission, which is a hyperspectral ocean color mission. And I'm very sure if you combine the three missions, the data sets from these three missions, so many new science, physics. I mean, you talk of anything, processes, the right side I just plotted to see that, in the background, there is an internal wave seen from the SAR mission. On the top, those those curved lines that you are seeing, they're the currents, surface currents from the SWOT mission. And on the right side, the color that you see is from the PACE mission. So how, the internal waves interact with the surface currents, and combinedly how it is impacting the ocean biogeochemistry, I'm very sure these three missions can unravel many of the hidden mysteries of the oceans. Thank you so much. And I thank Dr. Thomas G, his team, and all of you for for giving me this opportunity. And thank you all for your very, very patient listening. And thank you so much.
Thank you so much, ma'am. If you kindly allow, we'd like to ask our audience if they have any questions to ask to ma'am. Yes, yes, please.
I think that can be done. That should not be a problem. Once the data sets are available. So, at SAT, we have not done for this mission, but for other missions, yes. And for other, okay. So it's available. The data set is available. So once you have a long time series of data set, in large language model, one can get all these actually information also. In fact, many of the data analytics also can be done using that. Yeah.
To use their L-band data for forest biomass or forest stock assessment for such applications, are they allowing us to use?
Yes, this data set is freely available actually. And it's actually this mission is one of the mission which really works on the principle of open science, open data concept. So every data set is available.
Freely on the internet also?
Yes, on the cloud. NASA has put it on the cloud.
Late I saw somewhere in the Hindu newspaper that L-band data is not permitted, something like that. It's not correct?
No. It's a science mission. So it's a science mission as per their definition. So every data is available for the scientific community.
Thank you. Good to encouraging.
World community.
Yes.
But I think there is one small distinction of resolution over the globe and over India also.
No, sir.
No, sir.
No.
L-band is the whole globe. L-band is covering the whole globe.
Yeah.
And S-band is
3 to 8 meters. 3 to 10 meters is normal. Yeah.
S-band is only India
region,
and just surrounding. Indus.
So we also have global caravan sites. So over the global caravan sites, we get both the joint mode operations, and Indian region we get full S-band. And Arctic and Antarctic.
I was slide which you were showing that soil moisture for L-band and S-band match. This is what you are saying. In principle, why should they match?
Yeah. Yes. They are match. Yes, sir.
You are looking at different volumes or integrated columns.
Yeah.
Yeah.
Absolutely. Yes.
So my question further is there any effort to make earlier we always have been talking about so-called soil moisture profiles, like you talk about humidity profiles, temperature profiles, etc. in the atmosphere. Similarly, soil moisture profiles. So if you have, as you are saying that I have L-band, I have S-band, I have P-band, all those things. So on a synergistic use of these things for a particular site at a particular time, can somebody draw this soil profile?
So to answer your first question, when I mentioned that L and S band soil moisture match, they were grossly it was matching. We have not done the actual comparison with the actual ground truth observation that we need to do. And what is actually the thinking is, yes, you are right, sir. Because the penetration depths are different, so obviously there will be differences in the soil moisture estimation. What is our thought is maybe for a smaller, for the lower soil moisture content, one frequency might perform better than the other frequency. So these are all expectations actually, but our team is working on that to see whether the joint mode of operation can give us a better, the range also. See, one is the range capturing, another is the accuracy. So in terms of both, which combination is giving the good result? Now talking about this, yes, in one of my slides, sir, I showed that, we can take S band, L band, P band. So these three, and C band also. C also has a good sensitivity. It's not that it doesn't have a sensitivity. So I have my colleague is actually working on this aspect, that how to combine using the physics-based model, not the statistical model, because that may fail many times, or it might perform at times. So he's developing a model using the synergy of these frequencies to see whether we can get the profile. If not profile, at least good zone soil moisture, we can.
Madam, I have a question. Penetration capabilities of this L and P band, the comparison of that, any studies have been carried out?
I think theoretical studies are there, and with the biomass mission, which has been launched by ISA, so now we are trying to see using the biomass P band dataset and with the L and S band of the NISA. That is our next step actually, to see that how much penetration it is there. But theoretically, it is proven that P band has a maximum penetration. It can go below meter also, but L and S band has that kind of a restriction. Of course, L has a better penetration than S band.
Your group has not done any study.
Theoretically, yes. Yes, but not using the actual data.
This
Yes.
glacier surface velocity product which you have shown. Now, these velocity products are now available for small and medium-sized glaciers, or it is only for large glaciers like?
Even for smaller glaciers also, sir, because the resolution is so good. The resolution is 10 meters.
So, is it available for most of the glaciers in Himalayas now?
Yes. It is scene wise, sir. So wherever there is an acquisition, and over that acquisition, all these faces will be mapped. So it is scene wise, it is getting generated.
Our students can download
Yes,
this
sir.
velocity product from OSDEC site or some other?
No, from NRSC Bhunidhi site.
Okay.
Yeah.
Thank you.
So when you say about glacier, with the problem of glacier velocity, which people do with interferometric star, is it also being done with this?
Yes, sir. Yes, sir.
Now, I have a very basic doubt was there since last 10, 15 years, that originally always it was important to build an L-band star. But the L-band requires a much bigger heat shield. So we can't, ourselves, we're not able to go at it. Spaceborne. That's how we went to C-band. Then you can, all whatever you are. Of course, we went to a different phased area. Now, when you say S-band, we said that, okay, we will build a S-band. There was a lot of criticism that between L and S, in terms of the sensitivity to various Earth surface features, is not as high as between L and C. So the efforts in putting for doing S-band, except for the fact that we are building something, to what extent do you think of these results, from these results, that it has been worthwhile?
Okay. Yeah.
Uh-huh.
So, sir, what we have seen is, especially, I'll give you one example of above ground biomass for the forest. Okay, sir. So we used the data set from L band, and we used also from the S band. So what we could see is for the lower AGB value.
Okay.
Okay. For lower AGB values, the S band shows a better, sensitivity, better response. Okay. But forests being, the taller trees, I mean, wherever you have a higher biomass regions, so their L-band has a definite edge, no doubt about that. So we are looking for combining, I mean, S-band alone, if we say, there are very few applications where S-band alone can help. But if you combine S-band with the L-band data set, definitely many new and improved products can come out.
No, because 9 centimeter and 24 centimeter plus the emissivity related things are different.
Yes, sir.
So maybe jute, you might still do S-band, whereas forest you do with L-band,
Correct.
something like.
Absolutely, yes.
So
which one is better?
This is what, this is what is the science, sir. So our colleagues are working on this.
not enough that 5 and 9 centimeter wise penetration is different, but it also is important sensitivity wise and efficiency wise for a particular object. What is the efficiency difference between C-band and
S-band?
That is very important.
In fact, the sensitivity wise, S-band will be definitely better than C-band because it is between, L and C-band. So, yeah.
So, but I think there's a lot of
Exactly. So that is what.
No, but I thought you not you rushed through, but maybe because of the mixed audience. What exactly is the importance of sweep star compared to just star or scan star?
Yes.
That particular slide.
Yes, sir. Actually, I
But I don't think.
Okay. So can we go to that slide? Just one slide, yeah.
You tell me why.
Yes. Yes.
Time about what we can do. Yeah.
Yes. So actually, yeah, the previous one also. Yes. So if you look at the right hand side, okay. So what happens is there is an antenna, unfurled antenna. Okay. Below that there are transmit and receive feed circuits. Okay, sir. So in case of this antenna is working in two modes. During the transmit mode, it works in a different fashion. In the receive mode, it is working in a different fashion. Now, during the transmit mode, what it does is those beams, it is narrowing down, which is coming from the feed, and then it is making a very narrow beam width actually. If you look at that line, yellow line on the transmit side, okay, sir. So that narrow beam width is then beamed to the surface, Earth surface, in a broader area. So it looks at the surface. One beam is looking in the complete swath, so 240 kilometers swath. During the receive time, it is exactly working in an opposite way. So during the receive time, what it is doing is it is measuring the echoes from a smaller region from the ground, and then on the antenna side, it is making it as a bigger one because sigma, the noise square sigma naught also it has to increase, and then it focuses them to individual receive feeds actually. And
This is the through the electronics,
processing. Electronics and signal processing. On the top, what happens is there's a digital beam forming mechanism.
Okay.
So individual signals are then received and they are electronically combined.
Physically, if I had to do, you would have to tilt the whole aperture
itself. Yes. But in that one, there is a danger. If you do that,
there won't be orientation problem.
Angle and the pointing accuracy will be extremely poor. In this case, it is
digital beam formation.
Digital beam formation. Yes.
Embedded in.
And another very positive thing is, sir, when it is moving in an azimuth direction. Okay. There, the normal PRF, what is the pulse repetition frequency? Actually, the normal PRF, there will be some gap when it is moving.
Yeah.
In this case, there is a dithering happening. So PRF is not fixed. It is changing. So that it changes and then it fills those gaps. So in the azimuth also it is filling, and here it is looking at the figure. Yeah. So these are the newer.
No, I'm sorry. It is not that I'm asking questions only. You are out very.
Madam,
that some of these things are not explained.
I ask one question, madam. I have involved with the paleo channels mapping in the Thar desert area. I was with the Saraswati river mapping project. And these paleo channels in Thar, 50 to 100 meter depth there. Whether any of the SAR solution using any of the bands can meet my requirement.
What he's asking is because just like the old what you said in the desert, Sahara desert, one of the moisture which
Yes. Proxy, some proxy pencils, some proxy parameters, or paleo
if possible, one can look at
Yes.
or may not have that, but it is
No, but it's a good point. We can have a look at it.
possible.
It is possible. See, GPRs are used very widely for this ground penetrating radars, but about this, okay. Okay. So through soil moisture, then. Moisture very. Okay. Hmm. It's about 10% of the duty cycle for S band, and for L band it is 40. How much it is?
Oh, L. You're not collecting data on the other side of the globe because there is no power, or okay.
Downlink. Yeah, this is downlink.
The resource constraint. Yeah. And when you shift from say scan to high resolution, whatever, like our C-band radar satellite, the problem was, you switch on from scan mode to CRS, MRS, something. We used to have data gap of 425 kilometers. Are you having such constraints here, or you can switch in the same pass during same payload operation? You can switch from one mode to another mode.
So there are fixed modes here. There is no question of shifting from one mode to
Oh,
another.
yeah.
Yeah, it's a fixed.
At a time.
Yes.
Oh, that's awesome.
Yeah.
This has been one of my problems because in our C-band we try to put too much versatility, right? Finally, you operated only in one mode.
Yeah.
Correct.
That is
Fact.
all that-
Here the modes are fixed.
What
Yeah.
change is they suddenly turn on the whole
Science.
But this is constantly looking sideways, right?
Constantly.
Not like there, bias 42 degrees, such thing is not there.
Part of it is occupied the way.
Permanently looking at the same angle. Okay.
Madam, my question is about breaches in water bodies, especially high altitude. I heard that satellite data is used post events to say that there was some signatures. And the similar thing recently, Broad Peak, that avalanche causing landslide. So that a lot of people are resorting to adventure of with mountaineering as a passion. So NISR data anywhere it has been used currently to correlate that events which are recently happened. If data is collected prior to that from that region.
Yeah, because we are still not having the continuous time series of data. We are looking forward towards that, because unless you have a continuous 1 year, 2 years, 3 years of data sets, I mean, to say that such regions are actually some small drifts or some small changes are happening, this is what is the purpose of this mission actually, systematic coverage. So yeah, but
people spend lakhs of.
Actually, we have not been able to acquire so many cycles of systematic data. Although 25 cycles are over, but not in every cycle we have got the data. So now it is in a systematic mode actually.
Safety as one important thing you have mentioned. So that way, a lot of people who are investing a lot of money to really achieve their goals. So they are facing problems because more and more unexpected events are happening.
Yeah.
Maybe in that direction also, I think we should be collecting that archive.
And we hope to get all such signatures. Why did we just wait for some more time for the data sets to come? So that yeah. Yes. So that is why when people talk about that this is going to solve the problem of earthquake, actually, it's not possible to solve the problem. Yeah.
Monitoring surface before over a period of time. So that doesn't mean something to agree, but because they're all at a triggering point. Just like what you are saying for triggering for anything. No, sir. Deformation is not triggering alone. So deformation itself doesn't trigger, but deformation beyond a certain point might lead to that triggering it somewhere else. Deformation happens somewhere else.
Yes.
That is good.
You need to, I mean, maybe this will help us in modeling the earthquake in a better way, actually.
I remember very well. But no one used. So you're not able to get a conclusive evidence. Thermal data is used.
Yeah. Yes, I know. Postmortem. Yes.
China tried predicted all. That's why anomalies. They told 20% of China. See, they use GNXS.
Yes. Yes.
Based upon that, they ask students to talk.
Yes.
Warning, but that also is
Mm.
warning.
See, there are many such proxies. Total electron content is another proxy. Okay, which suddenly increases.
Yeah, that was the first one. Then even around and never happened. Hydrogen myself presented in the
Thank you so much.
Nothing happened.
Okay, students, yes.
The breaches happen not only, I mean, it's a regular deformation that is happening. When it reaches a level of alarm, we could always alert the nearby authorities to say that, to look at it, that there is a deformation happening. So the data can be used for that. Like you said, not a prediction for a
Breaking.
breach.
Moran breaking.
Right.
No deformation there.
No, but that study showed
There it is a pressure.
pressure.
Yeah,
Amount of
it's a
pressure
different-
is there.
Right.
Correct. And there are many factors, actually. There are many factors. Yeah, not one factor, yes. So it's a, yeah. No, but one thing is that this data set will be definitely helpful. Yes, please. Yeah, that's a very, very good question. Actually, there is a process called polarimetric decomposition. Okay, so it computes the Stokes vector. Okay, you have, let's say you have a quad pole data from each one, L band and S band. Okay, so you have HH, HV, VH, HV. That is one set of data. Another is, you have the RH polarization, and then RH and RV, and then you do some mathematical, decomposition, or it's called, I mean, it's mathematically called as decomposition only. You decompose them, and then three parameters are derived actually out of those decomposition. One is odd bounce, which is coming from the surface. Plane surface will give you odd bounce, some returns. Okay, if suppose the surface has a building kind of a thing, then you will get double bounce kind of a scattering. Okay, so that is another category of return. Third category of returns are from the forest, which is a volumetric scattering. Okay, so when you do the decomposition, you will get these three aspects: odd, even, and volumetric. So similarly, you do for L band and S band, and then you combine that to get the colors. Yes, because each one of them, they respond differently to the surface characteristics. When you decompose them, then those unique characteristics, unique interaction comes out from these combinations. And then you color code them actually. Color coding is a very normal thing. Yeah.
satellites, what cannot be done. Basically, it's an integrated effort. That is why, see, you take example of San Andreas. It's wired like anything, like you have hooked hundreds of things to monitor somebody's heart, The entire San Andreas fault zone is instrumented. Any small movement, the signal goes to either through a Wi-Fi router to a satellite dish and comes back in the center posting. And on the ocean bottom, in all the vulnerable areas, there are today bottom pressure recorders, with pressure transducers, which are used in launch vehicle kind of thing. And we have supplied to Incois. So any small plate movement on the bottom of the ocean is transmitted through the ocean buoy to satellite. Our own satellites are supporting that kind of analysis, that kind of data collection. So in a combined manner, we are able to predict some kind of movement, possibility of tsunami or no tsunami. So that's why, yeah, no, not post. If there is a small moment on the ocean bed, by the time it hits the shore, there is some time gap. Within that time gap, whether that is enough potential to create tsunami or not.
Yes.
So instrumentation on the ground, on the ocean bottom, and the data gathered ultimately through a satellite, entire data coming to the processing center, centralized, and then warning. These are all quite well operationalized, being operationalized. I think a lot of work has been done during our own time, the last 20 years. Yeah.
No, I not answer. I wanted you to read. There is a electromagnetic. After all, it's a microwave pulse, right? And microwave pulse, when it hits, you can have different polarized.
Thank